Hi students, now we will do servo design using LQR method. So I'm not using pole placement technique, I will be using LQR method, okay? For servo design. So not feeding my state only, but I'm carrying, I have C and I have an output that I want to control. So it's a servo design. So if you look to your system, again as we always doing, so I have three states, so third order system, so I can directly, for example, uh, saying Q is 3 by 3 as well, okay, and from here I know I have only one input, so my R is a scalar in general. Okay, let's start first by maybe 1 and 1 1 1, having zeros otherwise. Alright, also by looking at C you can understand it is one output, so you have one input one output system. Can I take Q as a scalar instead of taking it as this? How? Actually not. Q always will be like, even if I'm controlling one output, um, this is related to the number of states, always related to the number of states. Even so, now we will see that we care here, because we are doing servo design, we care only about this, which is related to this, which is x1, right? The x1. So we don't really need to change, put some importance or changing the weight on x2 and x3, because I'm feeding them back, but I'm not controlling them. I'm controlling this. Well, you can change them, but this will not affect your tracking, your control purpose. So then, yeah, you if you wish, you can change them, but you don't need. But always Q is related to the number of states. Alright, and I have here d equals 0. So then you know your problem. You start by this Q and this K. Check the controllability first. Check controllability of the system. Once it's controllable, then go and compute K using LQR. A, B, then QR. Starting by maybe equal weight 1 and 1, and at the end you need to choose Q and R to satisfy. You need to choose Q and R to satisfy your design goal. Satisfy your design goal, right? So basically that's the ultimate goal. You need to satisfy your design goal. Alright, so let me go over it. So here, well, I'm starting by equal weight of both, run it, then go to your servo design architect. Well, you need to build a servo design architect, and this is not a new thing for you. To do servo design, you have two ways, or you need to check the type of the system, as we studied, right? You have this. Those are the ways. What are the type of the system? What is the type of the system? Well, those are your pole. By using ig of a, I can find my pole. I can directly understand that. Well, I have numerator. I don't care. The denominator is s plus 1, s plus 2. So then it's a system of type 1. So I don't need integrator. This is my k, which is k1, k2, k3. What we learned in type 1 system, I feed all the state except whatever I want to control. Here I'm controlling y equal x1, right? Y equals cx plus d u, d equals 0, so then y equal x1, right? So I'm controlling only x1, and I will feed the remaining two state. Alright, and that's what I I did here. So I put K2, K3. Alright, so then we put K2, K3 in here and K1 in here. Look at this K1. I can write it like this, or I can put the value of it directly. I wish to write it this way because it's defined in my workspace. So then I make it this way, only one. And I define this way, 0. I have nothing here, 0 and K2, 3. Well, why I put 0? Because here I have 3 state. I'm feeding all my state. So I'm feeding all my state. So therefore you are feeding actually x1, x2 and x3, but because you are putting 0 for x1 is as if you are not feeding it. Just so if you want to only put k2, k3, then you should here put a demultiplexer and separate the states and only taking the second and third state, feeding them back. So here to get out, I multiply again by c here to get your y, and you are feeding your y, and therefore here you have k1. So here I have a step, and I decided at time 1 I will go to 1. This is my step input. So here I'm looking to the output, looking to the output of the to the states, looking to the control effort, all of those things are which you can look at. So here is your output. Well, if you are satisfied with that response, then you no need to change your Q and R. If you are not satisfied, then you need maybe to work more in here to change them. Is this, you need to ask yourself, you are the designer, is this Q and R chosen satisfy your design requirement? If yes, then yes, stick with it. If you wish, if you want to improve it, so you need to retune your Q and I. And remember here, you are not choosing again poll location. That's the beauty of. So maybe I want to improve the tracking, so put more weight on the tracking. So now when I go and you look at it how it is. Also you can look to the control effort, for example, and see how it is. All right. So okay. So now I will consider running it for Q equal 100 and look to the system how it looks like now, and your control effort how it looks like. So you are putting much more control effort, like 10 times more, but you are improving your tracking. Okay, so your settling time becomes less if you wish, because you remember increasing R, put more weight on R, this lead to making the system slower. So less weight, system will be faster. And here is an equivalent to having less weight. Remember the relative importance. So it has 1 by 1, like now 1 by 100. So like less weight on R if you wish. But also improving tracking performance. Um, just for the sake of comparison, maybe you can have it here. That's the first one. You look at it, how it is. What is the settling time even, and how it is now when I'm putting 100. Okay, so then if that's really something you can achieve, you can provide this control effort using from your motor doesn't saturate, and this is really what you want as a final response, so you get it this way. Also you can always look to the states and try to see them. X1 of course is the one that's moving to 1 because this is y equal x1, so we are doing servo design for it. Others should go to 0 within a settling time. So yeah, that's basically about this exercise. uh, you can even put here 2 more 0, or take this term or 0 here and divide here by 100, so this will give the same. Okay. Also you can try, if you wish, instead of 1 1 1 1, try 100 by 100 100 and here 100. Because of the relative importance, you will get same result as if it was as this one, right? So let's check. So here I'm putting 100 instead of 1, just replacing 1 by 100. You look, it's exact same result as what we had in case of 1. Look to them, they are exactly the same. So this is what we mean by relative importance. So you understand it now better. Okay. So also having 10,000 like 100 with 1 will give you same result as you have 100 with 0.01. So you have much lesser weight on the control effort, but you have more weight on the tracking performance. So you get even better tracking with, you see, with more control effort, assuming your actuator cannot saturate and can provide this, and you can. So maybe you have better response in that case. Yeah, that's it about this exercise. You see, the architecture doesn't change, just the way on which you are computing K is changed. Of course, you can always try to use control system tuner app, and control system tuner app use most likely the optimal control method, in which they don't choose pole location, but they do iteration of Q and R. Yeah, in control tuner. So now when you set your goals, that's internally what's going to happen. Like, you see optimal control, you cannot learn before learning state space control. So that you see same architecture as applied. You need to use gain matrices. So then you can also later on do it for type 0 system, um, for with observer. It will be the same with observer, with minimum order observer. So the way on how you computing K, just using LQR and having Q and R matrix that satisfy your design goals. But the architecture is still the same as in state space representation. So optimal control comes next after learning state space architecture.